Hey guys, we're going to do the bonding review day overview here. Bonding is going to be a pretty quick one. There's a couple main ideas, but really just getting a few basics is the key here. So first and foremost, chemical bonding is about the opposite charges attracting. So whether it's any type of bond, ionic, covalent, metallic, even IMFs, is about that attraction. So covalent, the reason it's being held together is that the protons from each of those two atoms are being attracted to the electrons in between, or those shared electrons. So it's not just the sharing of electrons, it's the attraction between those electrons and the protons. And that's if you were ever needing to explain the strength, which we'll look at right down here, it's all about the number of protons, or Zeph, or amount of positive charge in conjunction with the number of electrons as well. In an ionic bond, it is the cations and anions that are attracting each other. We're not sharing electrons there. One thing is gained, one thing is lost. We actually have a positive 1, 2, 3, 4 charge, a minus 1, 2, 3 charge that are attracting each other. And it is because of those opposite charges that it's attracting. It's not gaining, losing. It is the positive attracted to the negative. And then in a metallic bond, we have our metal atom. Its outer valence electrons are held very loosely. They're kind of wiggly around. A lot of times we call them a sea of electrons or mobile electrons there, but there's still an attraction between them. So it's not that the electrons just go wherever they want. They're attracted to those protons and to those positive charges from the metal atoms themselves, but they're attracted to the one here, they're attracted to the one there. So they're a little bit more free to move because the attraction is the same or very similar in lots of directions. So if you're asked to explain a strength of bond, it's not going to be a mathematical thing in terms of a calculation. It comes down to Coulomb's law. So right there, key idea in terms of a review sheet. And a key term here, Coulombic attractions, Coulomb's law, strengths of bonds, strengths of IMFs, strengths of attractions, whatever we're getting into there. The attraction's proportional to the magnitude of the charges, and we're going to hit that up with all of these. And inversely proportional to the distance. We'll also make sure we make sense of that. But the magnitude of the charges here means how many protons, or what is your Zeph, what is that positive charge of your nucleus, and then the negative charge comes from the electrons. A single bond has 2 shared. A double bond has 4. That's 4 things attracting the positives. So that is more negative charge attracted to the positive charge. It makes it stronger and does pull it closer together. With cations and anions, we are looking at and thinking about the charge of the positives and negatives, positive 1 to negative 1, positive 2 to negative 2, positive 3 to negative 3. The bigger those charges, the stronger that attraction. Even positive 2 to negative 1 is stronger than a 1 to 1 there because we have more positives. With the metals, we would think about what charge and how many valence electrons it would have. The mobile electrons are those valence electrons. Normally the electrons in the outermost s sublevel. Every now and then some d electrons can kind of wiggle around and be moving there too, but it's really the 1 to 2 s electrons that's being attracted to the positive charge there. So the more charge, the stronger it is, the more closely held they are. Inversely proportional to distance, that means the bigger the atoms themselves are, the farther away that positive nucleus, because that positive nucleus is right in the middle with a whole bunch of other stuff kind of blocking the way. So really small atoms are very close together, whether they're sharing or whether they're ions that are gained and lost. Those are going to be the strongest bonds. The bigger it is, the farther away those attractive units or those things are from one another, the weaker that is. Gold itself is a huge atom relative to copper and some other metals. It's got several more energy levels, several more sublevels that are full, all of those things. So that's why it ends up being a lot softer, more malleable, is that weaker charge from that extra size. So probably in terms of explanation, one of the key things here. Ionic bonding in first year chems, one of the things we kind of just say it happens and we move on here. I have talked about all of these things here, but once again, it is about the positive and the negative, not the gaining and losing, but the gaining and losing did happen. The metals lose, and this gets a little bit into periodic trends, which is good. Metals lose because they have a very low attraction for the electrons or a low ionization energy. The nonmetals gain because they have a high effective nuclear charge, a high attraction for electrons, a high electron affinity or electronegativity. So it's those difference of attractions for those electrons that cause the gaining and allow the losing. And then after it's done that, they bond. So once again, larger charges is stronger, smaller ions also charger. Oops, didn't mean to maximize myself there. I was going to move myself just to see because the distance is minimized. Sorry about that. Yeah, so that's metallic. We talked about this. The key thing is with metallic bonding, it gives us really unique bonding or properties associated with that. In covalent, it's two atoms kind of stuck next to each other. In ionic, the things are stuck in place because of attractions up, down, left, right, and front and behind. All of those opposite things attracting and holding into place, which is why if we go back here, these are really high melting points, strong attractions in all directions. They're brittle. They're really held firmly in place, but as soon as they shift around, they break apart. Metals are different. Those electrons are free moving. They're just as attracted to this as they are to that, so it can jump from one to the next, and then it can be attracted to the next and to the next with another electron kind of slipping into that hole, which allows them to conduct electricity or heat, the flowing of that motion, the flowing of the electrons. We can change their shape. We can make them malleable and ductile. I can take this ion and put it down here or over here, but still surround it with the sea of electrons, which gives it that. They're shiny because of the way it can absorb energy, allow the electrons to vibrate and release that again. But also here we have an alloy, a mixture of metals. So when I have a whole bunch of copper in a row, those are all held together by by metallic bonds. But I can take a copper out, drop a zinc in. Zinc still has some valence electrons that it can share and freely move around. We have now made an alloy. Because copper and zinc are right next to each other on the periodic table, they're very similar in size. So the copper just kind of fills in exactly where the zinc was. So it's like you have a whole bunch of apples lined up in the produce section of the grocery store. Take one out, put an orange in. It's pretty much the same arrangement. It doesn't affect the pyramid there. Nothing's going to fall down. But if you take out the apple and try to put in a grape, or take out the apple and put in the watermelon, that's going to change that pattern. That's going to change the properties. That is called an interstitial alloy. It changes the pattern or the way that those are arranged. And as a result, the interstitial alloy is quite a bit different in bond strength and in properties from a pure metal. A substitutional alloy, when we swap out copper and zinc, it has a lot of the same properties that zinc has and that copper has, depending which one you have more of. So those are some things there that are unique to the way that metals bond, is that it's not really associated with how many valence electrons there are or how many electrons it gains or loses. There are, with ionic bonds, obviously tons of things can form a plus one cation, but those are all different. But in metallic bonding, it's just kind of losing those outer ones. So a lot of things can act the same. You can mix in different ways, giving similar but slightly new properties. We spent most of our time on covalent bonding. It is the electrons between them. The single, double, or triple bond determines how strong it is, with some ideas of size as well. The things up at the top of the periodic table, whether we're talking ionic, covalent, or metallic, are the smallest, therefore closest together, therefore strongest bonds. But here, a single bond is long and weak because it's the fewest negative charges attracting to those two nuclei. Even if I have something that's maybe slightly bigger that we would think has a longer bond, if I go to a double bond with 4 electrons or a triple bond with the 6 electrons, they can pull them even closer. So nitrogen in 2, for example, that's a triple bond. It's a really short bond, and it's very close together and much stronger than maybe an oxygen or fluorine, which are actually slightly smaller atoms. The covalent bond holds the atoms together, but almost all of the properties for covalent are actually based upon the IMFs. So metallic bonding is based upon the way the bond forms, and the properties are associated with the bond itself. Ionic bonding is about the way the bond forms and the properties of the bonds themselves. But with covalent, it gets into IMFs. And we've got another day where we will review IMFs because they are huge in terms of explanations. Here it says to always draw the Lewis structure. We did one on our first mock exam where we had an incomplete Lewis structure, and it was asking about bond angle and lone pairs. Count up your electrons, throw your dots on there, do that either on scrap paper or on the paper you're going to take a picture of itself. If it's asking about bond angle, if it's asking about lone pairs, if it's asking if it's a single, double, or triple bond, if it's asking if the bond is longer or shorter, draw the Lewis structure by counting up the electrons so you can know how many electrons are involved in that. Some quick things with this is that we can kind of predict that the halogens over here on the right side of the periodic table, over next to the noble gases only need one more electron. They almost always form one bond. Oxygen and its family almost always forms two bonds, so two singles or a double. Nitrogen almost always forms three. Carbon almost always forms four, whether that's two doubles or four singles. But one thing we can be asked to explain, especially on Lewis structures that are given to us, is which one is better. And that comes back to formal charge. And if you want to go back and think about, or when you want to go back and review that, look at that. But it is the idea that they brought a certain number of electrons with them. So like oxygen had 6 electrons, you're 6 valence, excuse me. So then you're counting around each oxygen atom with the way that it's sharing its electrons. Does it have 6 electrons that belong just to it, or does it have more than 6? We can use formal charge to justify between two Lewis structures, because we're probably not going to have to draw, but they could give us 2 and ask, well, which one of these is better? We want the lowest possible formal charges. We want everything to have 0 if possible. We did some examples of that with CO2 when we did our bonding lab. And we also, if there has to be a negative charge, we want the smallest negative numbers possible, and we want them on the thing that's more low or negative. So like oxygen and fluorine are really good at attracting electrons, so they're most likely to have the extra if there has to be an imbalance for an extra one. When you are doing a drawing to try to think about the bonds, the lone pairs, the formal charge, they may or may not show all the dots in the drawing that they give you, kind of either in your head or even better on paper. Sketch all of the dots in, add them all up. It's worth that little bit of extra time, counting up all of the valence electrons going across the periodic table, 1, 2, 3, 4, 5, 6, 7, 8, and adding those up to make sure the drawing has the right number. With resonance, that's when we have Lewis structures, both of them that could be correct or both that are equal. So it's not just saying, well, I can draw this 2 different ways and this one works and this one doesn't, but the resonant, it's both that are correct, both that follow all the rules for them, and both that are exactly the same in all of the properties in terms of formal charge, in terms of the likelihood of where the bond will be. So 2 equivalent Lewis structures, every now and then they say, like, draw 2 structures, and they're really 2 of the same thing. A lot of times this happens when you're counting something up. It happens with the nitrate ion, with the nitrite ion. These are some that we drew, where it's a double bond on one side and a single on the other. There's no other way to draw it. And really it just kind of switches back and forth between double and single. But resonance, more than being able to draw the 2 structures, the definition and what it means is more relevant here. It is a compound that can't be completely represented by just one Lewis structure, that it's really somewhere in between 2 different versions that gives us the best picture of what's happening with the bonding. Because in that case, if I have a double here and a single here, it's not that I have a really short, strong bond and a long, weak bond, and then all of a sudden it goes the other way with really short and then long. Because those electrons are kind of we can say wiggling or alternating back and forth. It's almost as if we have a 1.5 bond on each side. A key thing to have, I have it as a link here, but there's no reason to open it, is just have all of your shapes. Have that sheet maybe even printed out, go back to the bonding chapter or click on it here, but it's going to show you all the bond angles for them. It's going to show you the names for the shapes. They may ask you that, but really way, way, way more than that. It wouldn't be just like, what's the shape of CH4 or that? It could be a complex molecule. Remember, if we're looking at something really big with carbons and hydrogens and oxygens everywhere, you can kind of focus in on one central atom, and they do that a lot with like a star or an asterisk and say, well, what's the angle around this? And all you're doing there is that is now your central atom. You look up, down, left, right, how many bonding regions, how many electron regions, and use the same rules from that chart that you would if it was a small molecule. That's the angle around there. You may or may not need to know exact angles, but there's no reason not to know them. Way more likely here, though, is the idea that, okay, we've got two things. I will open it up because it will be, I don't know if it opened for you. Sorry, it wasn't showing on my screen, but that was just the shape chart. If I have CH4, that's tetrahedral. We've got things on four sides. H2O is bent, a version of tetrahedral as well, but it's got lone pairs here and there. The lone pairs themselves, those electrons aren't being pulled away from the oxygen or aren't being shared by something else. So they actually repel better, or they have more negative power, if we will, to repel than the shared electrons. So not even caring about exact bond angles, but just thinking the more lone pairs you have, the more it kind of smashes the stuff together that isn't, or that is bonded. So that's a really good explanation. Well, why do these two bond angles differ slightly? Well, even though there's 4 electron regions in both cases, if some of those are bonding regions, it's going to bring them together. We kind of hit this a few times, talked about it in first year. I believe that it's on maybe some of the mocks even. But a polar bond is when I have two atoms themselves not sharing electrons equally. There's a difference in electronegativity. One's pulling a lot, one's pulling a little. They usually don't even care about exact values there. But if I have carbon and oxygen, they don't share it exactly equally because of differences in Zepf shielding and electronegativity. So the electrons are pulled more one way than the other. But a polar molecule is when, as a whole, I have a negative end and a positive end, or where they are being pulled to the left but not being pulled back to the right. A polar molecule is asymmetrical. That can happen because either you've got lone pairs, so there's some pulls from atoms in one way, but the lone pairs are not pulling on the electrons or pulling on that central atom on the other way. Or if I've got a carbon here and a chlorine here, chlorine and carbon don't pull on the electrons equally with one another. So we would be looking for asymmetry, and we would be looking for three-dimensional asymmetry. But that polar molecule is really, if you've got dots on your central atom, it's probably polar because there's not going to be a pull for electrons or a dipole there. Or if your central atom has multiple different elements, the first element pulls with a certain strength, the next element pulls with a different strength. They are not symmetrical. So even if I have a carbon with hydrogen top, hydrogen bottom, chlorine left, chlorine right, in 2 dimensions that looks symmetrical. But once we get into the real 3-dimensional shape, it's not anymore. And a really good thing to review polarity and molecule polarity and shape, if you kind of forget what it really looks like, is to go to PhET, P-H-E-T, shapes. That's a simulation. It's really quick and easy, and you just kind of add and remove lone pairs and bonds and single, double, triple bonds, and it changes the shape of your molecule. And it also has some polarity there. So PhET, P-H-E-T, there's a shape one, there's a bond polarity one, And while you're on there, you might find some others with the Gears law and some other stuff that's useful to just kind of refresh yourself. Some stuff you saw maybe in honors or regular chem, some stuff we used in AP. Just some visuals that are going to bring things back. But then a nonpolar molecule would be totally sharing everything equally. And polarity is super important because that leads into IMF questions. And since we've got 2 questions to test everything you know about chemistry, they're going to ask, how do you know if it's polar or not? And then what can you do with it? Exactly what I've tried to do on mock exam number 2. Put more things together where one leads to the next for the next. Even if you got a part wrong, you could guess or try to explain the next part. So there's a lot going on with bonding, but really if you can focus in on a few things, what is the bond? The attraction between the opposite charges, but what does that mean for each of the different types of compounds, which then does a lot to explain what the properties that they have. And then here with covalent, using the Lewis structure to do the next thing, to know about formal charge, to know about resonance, to know about not just memorizing shapes and bond angles. Put that on your sheet, have it there for you. Use that to make sense. Oh yeah, I remember that these are smaller angles, and that's all about those extra dots there. So I think that bonding will definitely be parts, but they'll be smaller parts. And a lot of times it's draw this Lewis structure, know this bond angle, maybe less of that, maybe more into the ionic as it transitions into something else, or more with the Y of the shape or the Y of the polarity to get into some IMF stuff.